There's one or two things that I would like to say about this construction a few moments ago. One, somebody asked me, yeah, but those new subsets of omega, they're already in M. No, they're new. The point is, okay, you can make this precise, but in the forcing method, you have your universe M, and you actually extend it by adding new sets. Where do those new sets come from? Well, from the genericity, but then you could ask, but how? If M is the universe that is there, where does the G come from? Well, that's what you may have seen in logic. The Lewin-Emskolem theorem tells you set theory has a countable model. And if you haven't seen that yet, then you will see that once in some model theory. So there is a countable model of set theory. Inside that model, there is something that tells itself that it is the power set of the natural numbers. Inside of M, there is no bijection between it and omega. M thinks it's uncountable. We, from the outside, that's a countable set. The point is, you have a model of set theory that is countable, that has countably many subsets of omega, and outside that model, we see plenty of subsets that are different from all the things in the model. And we could simply say, okay, let's take the model M and add this subset of omega to it and see what happens. If you do that carelessly, you might collapse the whole universe, because some subsets of omega will code a bijection between omega and the whole model. And you don't really want to do that. But if you build your your partial order inside M, then suddenly you only have countably many dense sets. And then the bare category theorem tells you there are plenty of filters that meet all the dense sets. And you only have countably many sets to avoid. Well, if you have a subset of omega in M, let's say it is a sequence of zeros and ones. Look at all the functions in P, the P that we looked at a few moments ago, for which there is an M such that Q0M is not equal to XM. This set is dense. Every element of P has a finite domain. So I can always find an M such that 0M is outside that domain and extend the function to get this effect. Oh, I have a stronger function that does this. This set is dense. Oh, G meets the dense set. That means that the X0 that we get from G is different from this thing in M. And by the same reasoning, as is X1, as is X2, as is X3, as is X4, and everything. And it happens for all the old subsets in M. So we get infinitely many completely new subsets of M. Well, we knew they were there because we could see them from the outside, but in the countable model M, they're new. The other thing, the set that I mentioned, not the enumeration, is in the symmetric extension M. And it's actually a subset of the reals. Okay, it's a subset of 2 to the omega, but that's the Cantor set. And so it's a subset of the real line. Without any infinite subset. Without any injection from omega into it. I think I mentioned this last week or the week before that. The characteristic function of this set is sequentially continuous but not epsilon delta continuous. It has points in the closure such that no sequence from the set converges to those points in the closure. And with genericity, you can actually make this a dense subset of, say, the unit interval. And then you have a really bad function, not epsilon delta continuous at all, yet it is sequentially continuous. It's not integrable, Riemann, in the sense, but it is sequentially continuous. So analysis goes wrong in that particular symmetric sub-extension, at least if you like sequences. Okay, now again we're going to take a leap of faith, and we're going to take our Mostowski model and we're going to subject it to the Jech-Sochor method. The Jech-Sochor method gives us the following. We're working in our universe U for the moment, and in the universe U we have a cardinal number, regular cardinal number kappa, that's bigger than the power set, the alphath power set of our A. And much like what Cohen did, what we're going to do is we have to stick our set A, we have to stick it in a generic extension of the curve. How do we do that? Using the forcing method and using a partial order that really looks a lot like the one that Cohen used in that, what I used in the previous hour. You can build a whole matrix of subsets of kappa, all new, not in the kernel, such that what? Well, nothing much, but what we're going to do is that the atom A is going to correspond to this set. And one of the things we'll realize in a moment is that this enumeration of this set will not be in the symmetric extension. So what is A tilde? So this is the copy of A in the symmetric extension. It's a technical device, but it's also useful halfway through the proof that we're going to look at. The proof of the no cardinality thing actually uses the way this model was built. And it uses at one point that we have this matrix of subsets of kappa. One reason why why don't I, for example, take A and identify it with one subset of kappa? I could. The point is, that is not, shall we say, atomy enough. We want A to be sort of completely random, and having it have many indistinguishable elements makes it technically easier to work with and get all the things done. For example, in the basic Frankel model, if you recall, the set A didn't have a linear order. In the Cohen model that I sketched a few moments ago, the set A does have a linear order, because you can order it lexicographically. You have subsets of omega, You look at the first place where they differ and make your decision according to yes or no, it's in there. So in that basic Cohen model, the set of, shall we say, atoms has a linear order. You have to do a bit more work to actually get atoms without linear order. And what is the work? Even in the Cohen model, if you say, I don't want a linear order for my atoms, you replace the individual subsets of omega that we made by sets of subsets of omega, sets of reals. And there is a theorem that says that the power set of the reals has no definable linear order. So you can get away with the family of all subsets of the reals doesn't necessarily have a linear order. You need the axiom of choice for that. So things get a bit hairy if you use this forcing method. You have to be a little bit more devious than just say, okay, let's take subsets of omega. You need a set of subsets of kappa of omega to destroy, for example, some linear orders here and there. But our set came with an external linear order, and the only reason why we have this, like I said, is technical later on. And the set A tilde will just be this. So that thing that I had on the picture, every one of those members of the A tilde is in itself a family of subsets of kappa, of size kappa, but without the enumeration. In the symmetric extension, the enumerations have disappeared. They're just outside that extension. So now we take the Mostowski set of atoms. It comes with a linear order. And what can we say about it? Well, we know this already. If we take enough power set along, then A tilde will be Dedekind finite as well. If you have a subset of A that is in V, and so what we say here also holds for A tilde in N. If you take a subset of A, then it is relatively simple. It's a finite union of intervals. Points count as intervals as well. How does that work? Well, it has a finite support, and then you just check if it has a finite support, so those finitely many points divide A into finitely many intervals, and for every one of those intervals, either it's completely inside of X or it's completely outside of X. By symmetry. And so the points individually can be an X, You can have the closed intervals or the half-closed open intervals or whatever, but they are the intervals bounded by the points in the support. Those are the ones that can contribute to X or not. One thing that we do need, okay, I must admit I didn't have time to create a sensible set of homework exercises, but I'll put one or two of these on so you can practice permuting again. Suppose you have a partition of A, so you split it into sets. If you partition your set into pieces, then only finitely many of those pieces are non-trivial. Of course, there will be intervals, there will be subsets of A, so there will be bits and pieces of intervals. But most of the members of the partition will be singleton sets. Well, if the partition just has finitely many things, then okay, fine. But if it has infinitely many members, then most of the members are just singleton sets. Here's another one, and I think it's too nice an exercise to do it here. So, and of course, this means there is a bijection between X and Y. So if you have two subsets of A in our permutation model V, if you know there is a bijection between them and the bijection is a member of V, then X and Y differ by only finitely many points. The symmetric difference is finite. So what the idea is that at many places this bijection has to be the identity. And only a few paired points can be moved in and out of X and Y. And that's it. So, but I mean, it doesn't say here that cardinality means anything, it just means there is a bijection between the two sets. More general, okay, this is slightly more general, but it's still true. Suppose you have 1 and k, so k plus 1 subsets of A. Everybody is in V, of course. And you know that there is a bijection between X and the union of the Y's, and the Y's are disjoint. Then this symmetric difference is finite again. And we're going to be using this in the end of the proof. But again, like I said, it's just nice enough to leave that as an exercise. As is the last nail in the coffin. Suppose you have a function with domain the natural numbers, and it's the values are finite subsets of A. Actually many n, because once you have one, you have many. But then you can, okay, I could formulate this more negatively. There is no function f with domain omega, which has finite subsets of A as its values, such that always fn has at least n elements. So every such function at one point must have a small set of a small value set. Why? Well, where does the n come from? Of course, from the size of the support. If you get beyond the size of the support of f, things go wrong, so to speak, and that is how the thing works. And so what are we going to do? And I see that this is going to go into next week. So what is going to happen? So assume that C satisfies Cantor's idea of a cardinality function. So if there is a bijection between x and y, then C of x and C of y are the same set. And C of x has the same, there is a bijection between x and C of x all the time. And although it sounds very grandiose that we have a cardinality function, what we're going to show is that the cardinality function is going to fail on the subsets of A. When I mean we're going to build an F, we're going to build such an F in N. All these things that I said about A are true about A tilde in N. Because just take enough power sets and then everything that we have over here is preserved by the isomorphism. Because a bijection between two subsets of A is a subset of A cross A, and so it's in the, I don't know, take 10 power sets and you're safe. I don't know, take omega power sets and we're really safe. So we know that in n, this is not going to happen for a tilde. And so what we're going to show, and we don't call it a tilde, we just call it a and everything. We will find that if we have such a function on the power set of a, then from that function we can really define unambiguously a function from omega to the finite subsets of a with that bad property. And we have to be careful that everything we do is definable or true, or in n at least. So occasionally maybe we need something symmetric, but I seem to remember that the symmetry is actually already gone. It gave us the model, and we simply work in the model without ever doing a simultaneous choice. That is what we have to avoid. Okay. I almost forgot. Yeah. Before we start, we need one more property of the model, actually two, but one, remember, no, I erased that, but I made the matrix U, right? It was an A by kappa matrix of subsets of kappa. And the members of A corresponded to, let's say, the rows of the matrix. The symmetry, the symmetric extension contains those A tildes, but it doesn't contain the enumeration of the A tildes. It simply contains those subsets as a family of sets, not as an indexed family of sets. How can we see that? Well, so I was tempted to write A cross kappa here, but that would be bad. U is almost A cross kappa, except that every one of those, rows in the matrix has no order. So we shouldn't really say A cross kappa, because that implies that the rows still have their nice ordering as kappa. We have taken the matrix and completely disordered the rows in the matrix. We kept the rows, but they have no order whatsoever anymore, as you can see here. If you have an infinite subset of U and an infinite subset of A, then there's not going to be a bijection between those two things. In particular, there is no choice function for the rows in the matrix. Which means that what we thought of as xa, 0, we don't see that anymore. Because you could say, well, you take the first column of the matrix, xa0, and so on. That's in bijection with A, there you go. No, that one has gone. It's no longer in N. It's outside of N. And any possible function that would let you pick for every A a subset of that row is gone. But also, say, 2-to-1 functions that might still be converted to bijections or something like that, they're all gone. And the other thing is, okay, this uses the forcing construction. If you want to prove this, you actually have to go to the forcing and see, oh yeah, right, that bijection doesn't exist. It's not something that comes out of the model as we have it. And the same thing or is it A cross kappa? Okay, I have to check that in my notes. So the Mostowski model, when you lift it into the by the forcing method, one of the things that you use is the supports, and you use finite supports again, as in the but you need finite subsets of A cross kappa, because when we built the matrix, there's going to be finite subsets there as well. And you can prove, and again, this takes forcing, that every hereditarily symmetric name has a minimum support. Just like we did last week, where we did all the going back and forth and the ordering and everything. You get minimum supports, and using that, you can again find an injective map of that universe. Okay, so I said you don't get the global linear order. You do, but not because of the p alphas, simply because of the construction. You can use this to find your global linear order. Ordinals, finite sets, and there you go. So, what do we have? We have this injective map. We have this strange statement about the infinite subsets of U and the infinite subsets of A. And from that, we should be able to build our function. Okay, I think what I'll do is I'm not going to be able to do the whole proof. Maybe it's better to start afresh next week, but I'll give you an idea of what's going to happen, and then we'll do the details next time. So what's going to happen? We're going to take n in omega, and we're going to define Fn. Okay, fair enough. But we have to make sure that the definition is uniform in n, because we want to define the function f all at once, because we say there is a function. When I say every n has a function value, that's not enough. I have to give you a formula, no matter how complicated, that will take any n as its input and take an fn, give an fn as the output. So I'm going to fix one n, but we're going to have to check in the end that this didn't depend on anything else but the n. Okay? Because here is one choice that we're going to make. Here, seemingly, is an arbitrary choice. We take a subset of A, whose complement has n many points. This we can do, because we don't need choice for that. We can simply use some existential quantifiers and everything to get that. Then what do we do? Take the special subset of what, I don't know what, the special set in N that is representative for all the sets that are in bijection with X. Oh, no more arbitrary choice. Because no matter what X I take, it has the same cardinality as, there is a bijection between it and the first X. Really? Yes. Take the n points in the complement, leave all the intervals into place, and put those points, chase those points around, and then you can take your X to your Y or whatever. Force you by putting it on the homework. We have our bijection C of X, our bijection F. We can take the F of C of X. Okay, there is no arbitrary choice anymore. I have the formula that defines F. So that big formula for the injection F is going to be instrumental in the formula that defines the little f. But still, that only depends on n so far. Now, what do we know about W? W is a subset of this three-dimensional space. It's fairly, how shall we say, it's a very irregular set. This is the this was the finite subsets of A, this was the finite subsets of U, and that's the ordinals, so fine. But remember, we have three sets in play right now. We have A, we have X, it's the complement of a set of finitely many points. N points to be exact. And what do we have? we have a bijection between x and cx. That bijection lives in n, because that's what we assume. So we have a bijection here, and we have another bijection, I don't know, here between c of x and w, and that's, no, it's given by f. So, fairly explicit. And what do we want to do? We want to, okay, now it's gone. We want to go to the situation where x and a are split into finitely many pieces. And no, we want to split x into finitely many pieces, like we had in the in one of those conditions on the cardinality thing. If you have two subsets of A and bijections between them, they were almost the same. And somehow create a complement in that, and then we'll be there. But how do we get that finite partition of x? Well, we're going to get the finite partition of w. And this is where the work is going to be. We have a well-defined, shall we say, partition of w. How? Well, we have this potato w here. We can slice it parallel to j cross the ordinals. For every member of I, we can take all the points that have that one as a first coordinate. So oh, sorry. It's a little bit more. I was getting ahead of myself. It's a little bit more intricate than that. We take, for every point in the in this product, j cross on, we take all the finite sets of I that act as a first coordinate e comma z belongs to w. And the first thing, that's a partition of what? Well, it's a partition of w. Oh, wait a minute, bijection, bijection, bijection. It's a partition of x. Together with the extra points in x, that's a partition of A. Oh, what did we know about partitions of A? Only finitely many cells have more than one point. Wait a minute, that means that only finitely many Z have more than one point here. Almost all of them have just one point. What are we going to show first? We're also going to show that only finitely many W's consist of one point. That means this looks pretty impressive, but there's only finitely many Z's here that actually contribute. Oh, wait a minute, that's way easier. I have only finitely many pieces of W, so I have finitely many pieces for X. Okay, it's still not good enough, because we want more structure on those finitely many pieces. And that's where the rest of the work, because what does it tell us? It tells us that we have a few places where we have one point and we have some other stuff going on, and that means that those W's we have to I don't know, mistreat them somehow to turn them into proper pieces of A. And then, because what is W? W is a family of finite sets. Literally, WZ is a finite is a family of finite sets. So what do we have? Well, we have a set here that is in bijection with, I don't know, a bunch of finite sets. And that means we still don't know enough of those pieces in the partition to be able to say something sensible about them. And then we have to unravel each one of those WZs, and we will. And then finally we get nice subsets of A that partition X. And then in the end, we can at one point say, well, here is a complement, and that complement is bigger than the complement of X, so there is our function f of n. And we have to be careful that every time when we do this, we are explicit. At every point in time, there should be no point where we say, oh, do something arbitrary. Because at that point we lose the function definition. Everything has to be according to the formulas that we have used so far. Okay, that's going to be next time. And saves me some preparation time next week. And I'll convert some of the remarks that I made into some problems for the last homework, because that's going to be the last homework, right? I can give you homework next time, but there's nobody to give it back to. Okay.
15 minutes.